These graphs from the chapter on sound show the air displacement, the particle speed, and the pressure for a one-dimensional sound wave travelling to the right. Note that the pressure P and the particle speed U are in phase. For a simple travelling wave, the ratio of pressure to particle speed is called the specific impedance of the medium, lowercase z. From Newton's second law, it follows that z equals density times the speed of sound. For water, the density and speed of sound are both much higher than for air, so z for water, or for human tissues, is about 5,000 times higher than for air. There's more about acoustic impedance at this link. What is the power transmitted through area A by the sound wave? From the definition of pressure, force F equals PA. In mechanics, we saw that power equals force times the velocity of its point of application, which in this case is u, the particle speed. In travelling waves, we defined intensity as the average power transmitted per unit area. The instantaneous power per area is Fu over A, which equals Pu. Using the specific impedance Z, we rearrange to substitute for the particle speed. So the instantaneous intensity is P squared over Z, or P squared over rho V. Let's take the sine wave with amplitude P sub m. As we saw in travelling waves, the average of sine squared over a whole cycle is a half. So the intensity I is a half P sub m squared over Z. In sound, we rarely use the peak pressure P sub m because the pressure only has that magnitude twice per cycle. Instead, we use the RMS pressure, meaning the root of the mean of the square of the pressure. By the way, RMS is also used in AC electricity and in thermal physics. Here, because the mean of sine squared is a half, the RMS pressure is just P equals P sub m over root 2. So finally we have intensity equals P squared over Z equals P squared over rho V. As we saw in travelling waves, intensity is measured in watts per square metre.